with useful libraries, algorithms, LLMs, supervised learning, neural networks, reinforcement learning, and more. Welcome to Crazy Fast AI and ML 101 tutorial. So hello world, I'm Super AI from Super AI the God. Super AI transforming holistic extraordinary game changer of the decade. It's almost the end of 2024 at the moment I'm preparing this tutorial. And a lot of people is talking right now about these AIs. More or less intelligent, like ChatGPT, Claude, Copilot, Gemini, Llama, Mixtral, Smaug, Grok, etc. So I think it's a good moment for you to learn more about them and how to use them. How they are created, how to improve them or even create others, better from scratch. In my previous tutorial I told you a little about Python language, and how to use it if you are a complete beginner. It's at my site, so if you need it you can check it. And this is my first tutorial in the introductory, Artificial Intelligence and Machine Learning series, in the age of large language models and multimodal models, and other impressive AIs, that are using more or less advanced machine learning techniques. This tutorial is a quick overview of the basic machine learning algorithms. During this series we'll talk about AI and ML, and you will find here some code you could use for simple, and more advanced bots using different machine learning techniques. This tutorial is super fast, so you can see how it is to learn matrix style like Neo, if you know what I mean. Anyway, it's fast, because I want to show you all there is in the whole course. Basic machine learning techniques and how to start using them, with the examples from the official websites. How to install everything you need and run it smoothly. And then I want to show you what's happening with AI and ML right now. And there is a lot happening as you probably know. A lot. Okay, now, something important for your safety. Be advised, because there will be a lot of fast changing pictures in here. If it's too fast you may slow it down or even stop for a moment. And one more thing before we start this crazy experiment. It's actually the second part of that course and I would recommend you check the first part, where I show you how you can start working with Anaconda, Jupyter Notebooks, etc. And where I show you in more details the first two algorithms, decision trees and logistic regression. If you've watched the first part you may skip the first couple of minutes of this tutorial. And now let's start this impossible to follow tutorial. See how long you'll last. Just be safe and don't overdo it. So here we go. Have fun. You can find this tutorial at my site, superai.pl. At the moment you watch it, it might look a little different than here, but it'll be mostly the same. If you want, you can read the short introduction I prepared for you. With it you can find the LLM you want, and ask it about artificial intelligence, machine learning, algorithm you want to learn about, and the AI might give you the code you might use at your computer. I'm showing you in the first part of this course how you can run this code but all in time. We'll use something called Anaconda for our coding. So, if you don't have Anaconda installed yet, you can watch my previous tutorial Python 101 for beginners, with an introduction to Anaconda, and install Anaconda. Now when we have Anaconda installed, here you can find the basic steps that can help you work with ML. I would recommend you to create something called environment for specific projects using different libraries. Here we start with Scikit-Learn library. Create environment for it with Jupyter Notebook and CMD prompt. Download the code from the website and open it. After you open the notebook, check if it's the right file. If you are using Jupyter Notebook for the first time, you can check how it works, learn some tricks to make your work easier and faster, and find the place we are at the moment. Here we start working with supervised learning. It's when your AI learns from labeled data. It tries to guess the label of the example, and learns from the mistakes thanks to the labels you provide. It can learn to classify things into categories. That's classification. Or predict continuous value, like with temperature, height. That's regression. Decision tree is one of these supervised algorithms, and can be used for classification and regression. Here we use it for classification. Now, we want the 1.5.1 version of Scikit-Learn library, because that library allows us to use decision tree with just one line of code. With our library installed, we can paste the code from Copilot, and celebrate. We've just trained our first machine learning algorithm. We are the champions. We can see how accurate our trained model is, and what mistakes it makes. Now we can install the second library we'll need. It's called GraphViz. This time on Windows we do it a bit differently. This library will help us get nicer looking trees. And in a moment you'll see what I mean. And we'll also need Matplotlib, so we'll install it as well. Oh, and here I had to change the version of Matplotlib to install, so we'll be using 3.9.2 version. And when you have it all installed, you can learn more about decision tree classification if you want, from the official Scikit-Learn website, and find the basic example to use, like the one we use here. The code works, but the outputted tree looks much better with our GraphViz library, and we can see all the decisions the AI makes to decide, if in this example, which type of iris flower is the one in question. Here we have 3 types of flowers, and a beautiful tree that, unfortunately overfits, learns too much from data. Achieving 100% accuracy might seem like a triumph, but it can indicate that the model is overfitting and not generalizing well to unseen data. To enhance the model's robustness, it's crucial to divide our dataset into training and test sets. We use the training set to build and fine-tune our model, and the test set to evaluate its performance on new, unseen data, ensuring it has learned effectively. We can analyze which classes the model finds most confusing and use this insight to fine-tune it. Adjustments could include modifying the tree depth, altering the minimum samples required to split a node, setting the minimum samples per leaf, etc. Now, the next classification algorithm we'll discuss is logistic regression. This model predicts the probability of a binary outcome based on one or more predictor variables. For multi-class classification problems, like classifying 3 types of iris flowers, it constructs multiple binary classifiers to determine the final class. In this context, our model has learned to classify these flowers. We can also examine the predicted probabilities for each class, which reveals the model's confidence in its predictions. To further improve our project, it's crucial to split our data into training and test sets. Additionally, we can utilize the confusion matrix to gain deeper insights into the model's behavior. Further refinements can be made by tuning various parameters. These adjustments will help us optimize the model's performance. Feel free to experiment with adjusting these parameters, but before you dive in, you should know that with just a single line of code, you can download a variety of datasets, including tabular data, simple image data, real-world datasets, generated datasets, and more. You can explore these datasets and test them with your preferred machine learning algorithms. And that's where we've ended the first part of this tutorial, so now, let's go further. The naive Bayes algorithm operates on the assumption that all features are independent of each other. Despite this simplification, it often proves to be highly effective in practice. We apply it here to our iris dataset. By adding a train test split, we can enhance our model and then evaluate its performance using a confusion matrix. It's worth noting that naive Bayes is particularly useful in scenarios with high-dimensional input spaces, such as text classification and natural language processing, NLP. The next algorithm you can see here is support vector classifier. SVC finds the optimal hyperplane to separate different classes in a dataset. If the data isn't linearly separable, it can use the kernel trick to transform the data so to make it possible. It identifies the support vectors, the closest points to the decision boundary, and maximizes the margin to improve generalization. SVCs are effective and robust against overfitting, but can be computationally intensive and require careful parameter tuning. With this simple example, you can see how it works. But to improve it and divide data into training and test set, we need to add more data so there is something to divide. We can also check it with our iris dataset in a way you've seen before, and see that it performs as good as the previous algorithms. Next we have SGD classifier. It is a linear classifier that uses stochastic gradient descent for training. It excels well with large-scale and sparse datasets. You can specify various loss functions such as logistic, hinge and perceptron losses, and adjust hyperparameters like loss, alpha and learning rate, to control model performance. Proper feature scaling and hyperparameter tuning are essential for optimal results. In this example, we define parameters such as loss type penalty and max iterations. To work with a train test split, we need to add more data. As before, we can test the model with the iris dataset. However, this time the model performs significantly worse than previous ones. So let's move on to the KNN classifier, which implements the K nearest neighbors KNN algorithm. A simple yet effective method. It works by identifying the K closest training examples to a new data point, and assigning the most common class among those neighbors as the prediction. You can specify the number of neighbors, K, and choose various distance metrics, such as Euclidean or Manhattan distance, to determine proximity. You can also control how neighbors are weighted with the weights parameter, choosing between uniform weighting or distance-based weighting. While KNN is easy to implement and interpret, it can be computationally expensive with large datasets, and selecting the optimal K value is essential for optimal model performance. Like previously, we can train it with one line of code, and check the results with another. Naturally, we divide the dataset into the training and test sets, and check how it works after that. And finally, we can check it with iris dataset, to see how it performs compared to other simple algorithms. Next, we have the random forest classifier, an ensemble learning method that constructs multiple decision trees using varied subsets of your data. For classification tasks, it aggregates the predictions from all trees to arrive at a final decision through a majority vote, enhancing overall accuracy and reliability. By selecting random subsets of features and samples for training each tree, it effectively reduces the risk of overfitting. Additionally, it offers valuable insights into feature importance, helping you understand which variables contribute most to the model's predictions. This time in our code, we create a synthetic dataset with 1,000 samples and 4 features. We add a train test split to enhance the model, and you can use the help function to explore other ways to improve it. And of course, we can check it with the iris dataset as well. Okay, now bagging, bootstrap aggregating, is an ensemble learning technique that boosts model performance by combining multiple base models, usually decision trees. It generates multiple bootstrap samples, random subsets of the data with replacement, and trains a separate model on each sample. After training, predictions from all models are aggregated, using majority voting for classification, or averaging for regression. Bagging reduces variance, prevents overfitting, and enhances model stability. However, it can be computationally expensive and decrease interpretability, especially with a large number of models. Our code demonstrates using a bagging classifier with a K-neighbors classifier on the iris dataset. It performs 5-fold cross-validation to evaluate the model's performance. Finally, it computes the mean accuracy score from the cross-validation results, without further improvements to bagging. Next we see gradient boosting classifier. That combines multiple weak models, usually decision trees, to build a strong model in a sequential manner. Each model corrects the errors of the previous ones using gradient descent. The algorithm gives more weight to better performing models to improve overall accuracy. It requires careful tuning of hyperparameters, like learning rate and number of estimators, to avoid overfitting. Although powerful, it can be slow and computationally intensive to train. In our code, we generate a synthetic dataset and then split it into training and testing sets. We train a classifier with 100 estimators and a learning rate of 1.0 on the training set. And finally, we test the same classifier with the iris dataset by simply replacing the dataset. Our next ensemble model is XGBoost. Gradient boosting trees and XGBoost build decision trees sequentially, where each tree corrects the errors of the previous one. XGBoost enhances this process with optimizations like parallelization, hardware acceleration, and efficient handling of missing data. The XGB classifier, a component of XGBoost, is designed for classification tasks and includes regularization to prevent overfitting, requiring careful hyperparameter tuning for optimal performance. This approach delivers high accuracy and scalability, but can be computationally intensive, especially with a large number of trees or deep models. In our code, we use the XGB classifier from XGBoost to create and train a model on the iris dataset. The classifier is initialized with 2 trees, each having a maximum depth of 2, a learning rate of 1, and a logistic regression objective for binary classification. And if you want, you can change some parameters to see how it affects the outcome, just like we did here. Have fun with that. The next model on our list is LightGBM, Light Gradient Boosting Machine. It is an efficient implementation of gradient boosting, designed for speed and scalability with large datasets. LightGBM grows trees leaf-wise, which can lead to improved accuracy, and automatically tries to prevent overfitting. Unfortunately, it requires careful hyperparameter tuning. We add it to our Scikit-Learn environment, and now the environment will include everything mentioned in our documentation. We'll install here 4.4.0 version of LightGBM, and 2.0.0 version of NumPy. Since I had a higher version of NumPy pre-installed with Scikit-Learn here, I need to downgrade it. And after this, it's good to restart the kernel, so that the correct version of the library is in use. It might be a little different in your situation, but I believe you can manage with it. And now, let's find an example to run. I found one using Iris dataset, but I think it's gone now, so you can try using another example instead. Anyway, here we can see how it performed. We loaded the Iris dataset, split it into training and test sets, and created a light GBM classifier. We fit the classifier to the training data and predicted the labels for the test set. We then evaluated the model's performance with a confusion matrix, and obtained a score of approximately 92%. Okay, now it's time for ADA Boost from Scikit-Learn. Adaptive boosting is used for improving the performance of weak classifiers. It combines multiple weak learners, typically decision trees with just a few layers, to create a strong classifier. It trains the model iteratively, giving more focus to misclassified examples in each subsequent round. By focusing on errors, it improves the accuracy of the model significantly over time. It's particularly effective with simple models, helping them achieve high accuracy without overfitting. In our first example, we created a synthetic dataset with 1,000 samples, trained a model with 100 estimators, and evaluated its performance. In the second example, we tested ADA Boost the same way with Iris dataset. We improved both projects by splitting the data into a training and test set. You can further improve it by changing the number of estimators, for example. Now, let's go to voting. Voting classifiers are ensemble methods that combine multiple models to enhance prediction accuracy. In hard voting, each classifier in the ensemble predicts a class, and the final prediction is the majority vote. In soft voting, each classifier predicts class probabilities, and the class with the highest average probability is selected. Hard voting is useful when classifiers only output discrete labels, while soft voting is more effective when classifiers provide reliable class probabilities. The voting classifier class in Scikit-Learn allows you to implement both types of voting. In our first example, we use hard voting algorithm with Iris dataset and 3 classifiers: Logistic, Regression, Random Forest, and Naive Bayes. You can see here the performance of each individual classifier and the ensemble. In the second example I found, we use soft voting for the same. This time we use decision tree, K nearest neighbors, and SVC. You can see here the decision boundaries of each classifier and the voting classifier, to compare their performance. We improve the second example by checking the scores. It's not much, but might help. And with the first example we improve it by adding more data, more features of Iris flowers, dividing data into training and test set before using cross-validation, and adding more classifiers to the mix. You can check how they perform. And finally we'll talk here about multi-class classification, multi-label classification, multi-output classification, and multi-output regression. We'll see here the last of our classification algorithms that doesn't use neural networks. Multi-output classification, and we'll also see multi-output regression algorithm. So, multi-class classification involves categorizing each sample into one of several classes, such as distinguishing between apples, oranges, and bananas. Multi-label classification allows each sample to be assigned multiple labels, like tagging a movie as romantic comedy or romantic comedy. Multi-output classification, or multitask classification, involves predicting multiple properties for each sample, where each property can have more than 2 possible values. Multi-output regression is a similar concept, where each sample is associated with multiple continuous target values. For example, predicting multiple attributes like price, area, and number of rooms of a house. In Scikit-Learn, these tasks can be executed with sklearn multiclass and sklearn multi-output modules. In our first example, we can see the code that demonstrates using a multi-output classifier to predict multiple target variables with a random forest classifier. It generates a synthetic dataset with 10 samples, 100 features, and 3 target variables. By creating shuffled versions of the target labels, the classifier is trained on the input features and predicts all 3 target variables for each sample simultaneously. In our second example, we use multi-output regression. We loaded the Olivetti faces dataset and split it into training and test sets. Based on the target labels, we trained multiple regression models: extra trees, K nearest neighbors, linear regression, and ridge regression, on the upper half of the faces to predict the lower half. Finally, we visualize the performance by plotting the true faces alongside the reconstructed faces generated by each model for comparison. This demonstrates how we applied multi-output regression to reconstruct partially missing images, leveraging different regression models in Scikit-Learn. And since we haven't added any improvements here, we can move on to classification with neural networks. So, we start with perceptron. A perceptron is a simple type of neural network used for binary classification. It processes inputs, applies weights, sums them, and uses an activation function to make a decision, while limited to linearly separable problems. It laid the groundwork for more complex neural networks. You can read at Scikit-Learn site how you can use it with various parameters. We'll use it to recognize handwritten digits. In this example, we've loaded the digits dataset, initialized a perceptron classifier, and trained the perceptron model using 5 lines of code, and we got 94% accuracy. Of course, we can improve it by dividing data into a training and test set, and check the confusion matrix to see how the model performs. We can also check it on the Iris dataset, and see that we get around 87% accuracy on the test set with this model. Not bad, not great. Okay, so now we start moving to more advanced of the basic algorithms, a multi-layer perceptron. MLP is a type of artificial neural network with an input layer, one or more hidden layers, and an output layer, where each node is connected to every node in the next layer. MLPs use nonlinear activation functions to model complex relationships, making them suitable for classification and regression tasks. They are trained using backpropagation to adjust weights based on errors between predicted and actual outputs, forming the foundation of deep learning models. In this basic example, we create a synthetic dataset with 100 samples. We split the dataset into training and testing sets, ensuring the class proportions are maintained using stratification. Finally, we train a classifier, setting a maximum of 300 iterations to achieve convergence. Then we test the model with Iris dataset and achieve almost 95% accuracy. Okay, so let's move on to creating simple neural network with TensorFlow. But before we do it, let me tell you a couple of things about this neural network thing, and that's so-called deep learning. Neural networks are machine learning models inspired by the human brain, designed to recognize patterns and make predictions from data. They consist of layers of interconnected nodes, or neurons, where each node processes input and passes its output to the next layer. Deep learning refers to neural networks with many layers, often called deep neural networks, which enable the model to learn more complex patterns. There are different types of neural networks for specific tasks like convolutional neural networks, CNNs, which are great for image data, and recurrent neural networks, RNNs, which work well with sequences like text or time series. Even more specific type of neural network, called a transformer, is used in ChatGPT and other large language models. LLMs. Transformers use a mechanism called self-attention to process sequences more efficiently, enabling them to understand and generate human-like text. This capability makes them highly effective at tasks such as conversation, summarization, translation, and answering questions. We'll use here all these algorithms with libraries like TensorFlow, PyTorch, FastAI, and Hugging Face. And now we'll create our first neural network with TensorFlow. And by create, I mean we'll copy and paste the code from their website. TensorFlow is an open-source library developed by Google Brain for machine learning and AI. It helps you build and deploy models for a wide range of tasks, from data processing to large-scale machine learning projects. To get started, we'll set up a new environment called TensorFlow ENV, with Jupyter Notebook and CMD prompt. And we'll reopen our file with this tutorial in that new environment. I'll install TensorFlow 2.16.2 version for Windows in my environment, but you can try other versions that fit your needs. Now, with this version I won't be able to use my GPU, that is Graphics Processing Unit, which is a specialized processor designed for parallel computing, and crucial in advanced machine learning, as it significantly speeds up the training of complex models. I tried various ways to make it work with TensorFlow and this example, but after some time I gave up. If you want, you can try make it work on your own, and you will see me using that GPU in just a couple of minutes with PyTorch. Anyway, let's get back to our example. We'll use the MNIST dataset, which contains 70,000 handwritten digits, and is often used to train image classification models. So we imported TensorFlow and loaded the MNIST dataset, normalizing the data. We built a neural network model with 4 layers, a flattened layer, a dense layer with 128 neurons and ReLU activation, a dropout layer, and a final dense layer for the output. We made predictions using the model and applied softmax to convert the raw output to probabilities. We defined and compiled the model with an appropriate loss function and optimizer. Finally, we evaluated the model's performance and added a softmax layer to output probabilities for predictions. The accuracy we achieved is almost 0.98, which means the model correctly predicted the test data over 97% of the time. This is an impressive accuracy, don't you think? And now we'll use a simple neural network with PyTorch. PyTorch is an open-source deep learning framework developed by Facebook's AI research lab. It provides flexibility and speed for building and training neural networks. It offers dynamic computation graphs, allowing for immediate feedback and easier debugging, which makes it particularly popular for research and experimentation. With its powerful tensor library similar to NumPy but optimized for GPU acceleration, PyTorch enables efficient numerical computations essential for training complex models. Additionally, PyTorch's rich ecosystem includes tools like Torch Vision for image processing, and Torch Text for natural language processing. We'll create here a new environment for it we'll call PyTorch ENV. As usual, we'll add Jupyter and CMD prompt to it and we'll reopen our tutorial file. And we'll install PyTorch. To do it, you should follow the instructions on their site depending on your system and the version you want. Here it's 2.4.1 with CUDA 11.8. We also get here Torch Vision 0.19 and Matplotlib 3.9.2. And now we can check if we are using our GPU. And yes, we are. That's great. So let's check the example from their site. In here we import necessary PyTorch libraries and download the FashionMNIST dataset. That is a collection of 60,000 28 by 28 grayscale images of 10 different clothing categories, commonly used for training and benchmarking machine learning models in image classification tasks. Converting the data into tensors, we create data loaders for both the training and test datasets. We define a neural network model with a flattened layer, 3 dense layers and ReLU activations. The model is trained using a specified loss function and optimizer, and then evaluated on the test dataset to determine its accuracy. Finally, we save the trained model, load it, and use it to make predictions on new data. For improvement, we can just visualize our tested examples, and see that model sometimes correctly predicts that. This is an ankle boot, and sometimes it's wrong like here when it predicted pullover, and this is a shirt. And that's it. Another working example that awaits for your own testing and modification. Have fun with it. Okay, so now, let's try using a CNN with TensorFlow in the environment we set up earlier. CNN means a convolutional neural network, which is a deep learning model designed for processing visual data, such as images and videos. CNNs mimic the human visual system structure, using layers to automatically extract features from input images, starting from simple patterns like edges to more complex shapes and objects. The core component of CNN is the convolutional layer, which applies filters to the image to identify patterns. It applies a convolution operation to the image using small matrices called filters or kernels. These filters slide over the image, performing calculations to detect features like edges and textures. Each filter highlights different patterns, and the result of this process is a feature map, which shows where these features appear in the image. CNNs use pooling layers to reduce the image size, making the model more efficient while retaining important information. Over time, CNNs have been improved with techniques like batch normalization, dropout, and advanced architectures like ResNet or Inception, to enhance their performance and prevent overfitting. Due to their ability to recognize complex patterns, CNNs are widely used in applications like image classification, object detection, and facial recognition. In our example, we use a CIFAR10 dataset that contains 60,000 color images, each of size 32 by 32 pixels, and these images are divided into 10 different classes. The model comprises 8 layers. After compiling the model with the ADAM optimizer, we train it for 10 epochs. Training a model for an epoch means that the model processes the entire training dataset once. This involves feeding the training data through the network, calculating errors, and updating the model's weights accordingly. After that, we plot the accuracy and evaluate the model's performance on the test dataset, reporting the final test accuracy. The goal is to improve the model's accuracy and performance with each epoch, as it learns from the data, and at the end our accuracy is over 70%. In other words, we can say that out of every 100 images, the model was able to correctly identify 70 of them. If we add one more layer and train the model for 10 epochs, we can get even higher accuracy. Now, let's look at an example of a CNN created with PyTorch using the CIFAR10 dataset. It's not exactly the same as the one created with TensorFlow, but you can modify them to make the models identical. This way, you can compare the differences between the two libraries. Okay, now, we'll use a model called ResNet. ResNet, residual network, is a type of deep convolutional neural network that includes shortcut connections, which allow the model to skip layers. This helps address something called the vanishing gradient problem, making the network easier to train and enabling it to learn more effectively. Even in deeper architectures, we'll be using ResNet 18, which has 18 layers, but there are versions with hundreds of layers for more complex tasks. This time, we won't need to train the model, as we'll use a pre-trained ResNet model that is already set up for use. Other pre-trained models you might be familiar with include LLMs like ChatGPT, which you can also download and use directly without needing to train them. So, as you can see, we can use pre-trained models right after downloading, and they could be very accurate. But we can also improve these models. Here we'll download ResNet 34 and fine-tune it with FastAI library. First, we'll create the new environment for this library. FastAI is a high-level Python library built on top of PyTorch. That simplifies the process of training deep learning models, especially for tasks like image classification, natural language processing, and tabular data analysis. It is known for its simplicity and ease of use, making it accessible even for beginners. It provides easy-to-use abstractions for complex machine learning workflows, allowing users to quickly build, train, and deploy models with minimal code. It provides high-level components for practitioners to quickly achieve state-of-the-art results in standard deep learning tasks, and low-level components for researchers to build new approaches. FastAI emphasizes best practices and leverages pre-trained models and transfer learning to achieve high performance with less data and computational power. We'll use our GPU with this library. In our first example from their site, we use ResNet 34 and fine-tune it to create a classifier for cats and dogs. As shown in the second example, using this library is incredibly easy, and fine-tuning pre-trained models is fast and straightforward. Despite its simplicity, it allows you to achieve state-of-the-art results. FastAI automatically searches for the optimal learning rate by plotting the loss as a function of the learning rate, helping you identify the best value to use for training. It can create an interpretation object, which allows you to analyze and visualize the model's predictions, including errors, confusion matrices, and other evaluation metrics. Based on the trained learn object, you can even plot top losses if you want. This library is a really good choice for beginners. In this example from their site, you can even see how easy it is to create a multi-label classifier. They use here Pascal 2007 dataset, which was a widely used benchmark in computer vision, consisting of 20 object categories and annotated images for tasks like object detection, segmentation, and classification. I encourage you to have some fun with these examples. You can easily improve a model in FastAI by adjusting the learning rate, applying data augmentation, using pre-trained models, experimenting with model architectures, increasing epochs or batch size, applying regularization, like dropout or weight decay, and fine-tuning with differential learning rates. And now let's use the ResNet 34 architecture with UNet, with the help of FastAI library for image segmentation. That segmentation in computer vision involves dividing an image into distinct regions. To simplify analysis, semantic segmentation assigns a class label to each pixel, while instance segmentation distinguishes between individual objects within the same class. Panoptic segmentation combines both approaches, providing a holistic understanding of all objects and background elements in the image. The UNet architecture is a convolutional neural network designed for segmentation tasks. Features a U-shaped structure with a contracting path for context extraction, and an expanding path for precise localization. Skip connections between these paths preserve spatial information, allowing UNet to effectively capture both global context and fine details. This makes UNet particularly well suited for semantic segmentation tasks, such as pixel-level classification. The FastAI library simplifies the training of UNet models for segmentation tasks. With minimal code, you can quickly download datasets, create data loaders, and set up a UNet model with a ResNet backbone, making it easy to fine-tune the model for specific tasks. In the first example from FastAI's site, we downloaded and extracted the CamVid tiny dataset, and created a segmentation data loader. We then defined a UNet model with a ResNet 34 backbone, and fine-tuned it on the dataset for 8 epochs. Finally, we visualized the model's predictions alongside the ground truth. Segmentation can be used in a variety of tasks, such as aiding self-driving cars, so sometimes it's good to dive deeper into what's wrong with the model, by examining its worst outcomes or decisions. And we can see these top losses in our second example. Okay, so now let's create a new TensorFlow environment for RNN. This time we'll use TensorFlow 2.15.1. Great, so let's talk about these RNNs. RNNs, recurrent neural networks, were designed to process sequential data, where the output at each time step depends on previous inputs, making them ideal for tasks like natural language processing and time series analysis. A significant advancement in RNNs was the long short-term memory architecture, LSTM, which addresses the vanishing gradient problem by using gates to control the flow of information, enabling the model to capture long-term dependencies more effectively. The frameworks we used here before, TensorFlow and PyTorch, provide robust tools for building and training RNNs, including LSTMs and GRUs, while FastAI simplifies the process with high-level abstractions, enabling fast experimentation. Pre-trained models, such as a WD-LSTM and transformer-based models like GPT-2 and BERT, are available in these libraries, allowing users to fine-tune models with less training time and better performance on specific tasks. Despite the rise of transformer-based models, simpler RNNs, particularly LSTMs, remain a powerful choice for sequential data tasks, due to their ability to model temporal dependencies effectively. We use TensorFlow 2.15 here, because that's the one I was able to make work with this example. In this example, we load the IMDb reviews dataset from TensorFlow datasets, and prepare it for training by shuffling, batching, and prefetching the data. We then use text vectorization to tokenize the text data, creating a vocabulary of 1,000 words, and convert the text into sequences of integers. A simple RNN model, instead of LSTM, as modified in the code, is built with an embedding layer, a bidirectional simple RNN layer, and dense layers for binary classification. The model is compiled with binary cross-entropy loss and the ADAM optimizer, and then trained for 10 epochs on the dataset with validation on the test set. After training, the model is evaluated on the test set, and the accuracy and loss curves are plotted, followed by predictions made on a sample text. The model predicted with 74% probability that the input, the movie, was cool. The animation and the graphics were out of this world. I would recommend this movie, is a positive review, so I think it's okay. If you want, you can test the model with other sentences. Okay, so now let's try simple RNN created in PyTorch, from the example from their site. In this code, we build a character-based RNN to classify names by their language of origin. We start by loading text files containing names categorized by language, converting them from Unicode to ASCII, and creating a mapping of letters to one hot encoded tensors. The RNN architecture is defined with input, hidden, and output layers, and we implement a training loop to optimize the model using negative log likelihood loss, NLL loss. After training for a specified number of iterations, we evaluate the model's performance using a confusion matrix and visualize the results, allowing us to assess its accuracy and make predictions on new names. Finally, we demonstrate the model's ability to predict the language of several example names, such as Dovesky, Jackson, and Satoshi. As you can see, the code works quite good. Now, let's go back to our TensorFlow example and try using LSTM instead of simple RNN. To make this example work with LSTM, we just need to change one line of code. Instead of Keras, layers, simple RNN, we type Keras, layers, LSTM, and that's it. Now you can check if LSTM performs better. You can test it with longer reviews to see which RNN architecture works better, the simple RNN or the LSTM. And if you want to improve it even further, you can train it for a little longer. And now let's use LSTM with PyTorch. In this example, we initialize an LSTM-based tagging model for sequence labeling tasks, specifying the embedding dimension, hidden layer size, and the number of unique words and tags. We set up a negative log likelihood loss, NLL loss, function and a stochastic gradient descent, SGD optimizer, to update the model's parameters during training. The model's performance is evaluated before training by passing a sample input through it, to obtain initial tag scores without calculating gradients, allowing us to see how the model performs before learning. During the training loop, we process each sentence in the training data by preparing the input and target tensors, performing a forward pass, calculating the loss, and updating the model parameters using backpropagation. Finally, after training, we evaluate the model again by passing a sample sentence through it, showing how it has learned to correctly predict the sequence of tags corresponding to each word. Great! Now let's create another FastAI environment with Python version 3.9, FastAI version 2.7.15, and PyTorch version 2.3.1. And let's check their example in which we utilize the FastAI library to create a text classification model for sentiment analysis on the IMDb movie reviews dataset. We load the data using text data loaders, set up an AWD-LSTM model with specified dropout and accuracy metrics, and fine-tune the model over 4 epochs. After training, we use the model to predict the sentiment of various movie review sentences, demonstrating its ability to classify both positive and negative sentiments based on the input text, such as, I really like that movie, and I didn't like that movie. And now let's move to transfer learning. Transfer learning with the FastAI library involves using pre-trained models, and fine-tuning them for a specific task, allowing for faster training and better performance with limited data. In the first code example, we load the IMDb dataset, create a text data loaders object for sentiment analysis, and initialize a text classification model using AWD-LSTM. We fine-tune the model over several epochs, and evaluate its performance by predicting the sentiment of sample movie reviews. Now, moving to the second code example, it focuses on building a language model first, using the same IMDb dataset and AWD-LSTM, which can enhance the performance of subsequent tasks. After fine-tuning the language model, we save the encoder and use it to initialize a text classifier. This enables the classifier to benefit from the language model's pre-trained knowledge, improving the sentiment analysis task with the same dataset. By leveraging transfer learning, the model benefits from the knowledge gained from training on a large corpus, making it more effective at understanding and predicting movie review sentiments. Another specific task we can do with FastAI library is tabular learning. Tabular learning, with FastAI, simplifies the process of training machine learning models on structured data, by automating tasks like pre-processing, model creation and evaluation. In the first example, we load the adult income dataset, create data loaders with categorical and continuous variables, and apply pre-processing steps. We then train a model using tabular learner for 3 epochs and evaluate it based on accuracy. The second example also loads the same dataset, but includes additional data exploration with pandas, splitting the dataset into training and validation sets. It then creates a tabular pandas object and demonstrates batch visualization, model training for 1 epoch and making predictions. The main difference is that the second example includes a more detailed data inspection and splitting process. Additionally, it shows how to visualize data batches and make predictions on new rows. And now let's move to transformers, which are the cornerstones of today's LLMs like ChatGPT, Claude, and others. The transformer architecture introduced in the 2017 paper, Attention is All You Need, is a deep learning model designed for handling sequential data such as language, and revolutionized natural language processing. It utilizes a self-attention mechanism to weigh the importance of different words, or elements in an input sequence, capturing long-range dependencies and context more effectively than previous models, like RNNs and LSTMs. The architecture is composed of an encoder-decoder structure, where the encoder processes input data and the decoder generates output, allowing for parallel processing and faster, more efficient training. This parallelization enables transformers to handle longer sequences and large datasets, making them significantly more efficient and scalable for tasks like machine translation, text generation, and language modeling. Transformers have become foundational in AI, driving advancements not only in NLP but also in computer vision and multimodal learning. They are crucial in state-of-the-art models like BERT, GPT, Claude, and other LLMs, which have set new benchmarks in contextual understanding and generation, revolutionizing tasks across various domains. The widespread adoption of transformers has led to groundbreaking developments in language understanding, from conversational agents like ChatGPT and Claude to systems capable of reasoning, summarization, and even multimodal interactions. We'll create here a very simple transformer from PyTorch example. I wanted to do it in our PyTorch environment, but I encountered some problems, so I had to create a new environment. I called PyTorch 231. In this new environment we install PyTorch 2.3, Torch Vision 0.18, Torch Audio 2.3, and other related libraries such as Matplotlib, Portalocker, Torch Data, Torch Text, and Spacey. We also download language models for English and German from Spacey. Follow the instructions in the tutorial to create this working environment. In this, a bit longer example, we implement a sequence-to-sequence model for machine translation using the transformer architecture. We first prepare the multi-30K dataset by tokenizing and building vocabularies for both the source and target languages, German and English, followed by defining the transformer model, which includes positional encoding and token embedding layers. We then set up training and evaluation loops, compute loss using cross-entropy, and perform optimization through backpropagation. Finally, we use a greedy decoding strategy to translate sentences from the source language, German, Ein Group von Menschen steht vor einem Igloo, into the target language, English, a group of people stand in front an auditorium, and some other sentences, and we have our transformer working so-so. Moving further, let's talk about our next model, BERT, bidirectional encoder representations from transformers. Introduced by Google in 2018, was revolutionary in transforming natural language processing by using a bidirectional approach to understand the context of words in a sentence, considering both the words before and after a target word, allowing it to understand context more deeply than traditional models that process text in one direction. Built on the transformer architecture, BERT processes entire sequences of words simultaneously rather than one at a time, enabling more accurate contextual comprehension. Its architecture allowed it to set new benchmarks for various NLP tasks. While BERT was groundbreaking at the time, newer models built thanks to it and using transformer architecture, like the GPT family from OpenAI, Claude from Anthropic, Llama from Meta, and Gemini from Google have since advanced the field, improving efficiency, scalability, and versatility. Although not as revolutionary today, its impact on AI and NLP remains significant. We'll use here an example from TensorFlow's site, and because this example is quite old we'll have to use TensorFlow version 2.10, and Python version 3.9. You may try using newer versions, but for me the combination you see here was the only one that actually worked. In this example the code starts with downloading the IMDb dataset, cleaning it by removing unnecessary folders, and selecting a BERT model along with its associated pre-processing model from TensorFlow Hub. It then pre-processes a test sentence using the selected BERT tokenizer. The text is passed through the BERT model to obtain sequence and pooled outputs for sentiment analysis. A custom classifier model is built using the BERT encoder, with dropout applied for regularization and a dense layer for classification. The model is compiled with the ADAM-W optimizer and binary cross-entropy loss function. It is then trained on the training dataset, validated on a validation set, and evaluated on the test set. Training and validation accuracy and loss are plotted over epochs. After training, the model is saved and reloaded, and predictions are compared between the saved model, the in-memory model, and the serving model to ensure consistency. For example, after training, when the model evaluates sentences like, "This is such an amazing movie," and "The movie was great," it gives high scores, around 0.99, indicating strong positive sentiment. Conversely, phrases like, "The movie was terrible," receive very low scores, showing strong negative sentiment. The model is effective at distinguishing between positive, neutral, and negative sentiments based on the scores it assigns to each sentence. Great, so now let's finally see that GPT model. We'll use here the code from FastAI's website. This code loads a pre-trained GPT-2 model and tokenizer, tokenizes input text, generates predictions using the model, and fine-tunes it on a custom dataset for text generation tasks. But before we run the code, generative pre-trained transformers, GPTs, are a series of language models developed by OpenAI, designed to generate human-like text based on input prompts. These models are auto-regressive, generating text one token at a time while conditioning each new token on the previous ones. Each iteration of GPT, from GPT-1 introduced by OpenAI in 2018 to GPT-4, has seen increased parameters and capabilities, with the models effectively capturing context and relationships between words using self-attention mechanisms. The provided code demonstrates how to use the GPT-2 model from the Hugging Face Transformers library for text generation, so it's not a classification algorithm, but it can be used for classification, I think. It begins by importing the necessary libraries and loading a pre-trained GPT-2 model and its tokenizer. The input prompt is tokenized into numerical IDs, which are then converted into a tensor suitable for model input. The model generates text based on this input tensor, producing a continuation of the original prompt. The code also prepares a dataset using FastAI's text tools, tokenizes text from the Wikitext tiny dataset, and sets up training and validation data. A custom tokenizer class is used to process the text, and a FastAI learner is created to train the GPT-2 model. The model is trained using a learning rate finder and one-cycle training schedule. And finally, the generated token IDs are decoded back into human-readable text, allowing users to see the output created by the model. Here we can see that the GPT model generates a continuation of the prompt. A unicorn is a magical creature with a rainbow tail and a horn. Producing the output, a unicorn is a magical creature with a rainbow tail and a horn at its shaped head. It is a member of the Ankh family, showing the model's ability to creatively extend the text, though it introduces unknown tokens Ankh when it encounters words outside its vocabulary. We can also see some other examples here. To adapt this code for classification, you would modify the model to use a classification head instead of the language modeling head, fine-tune it on labeled training data, and then use the model to predict class labels based on input text instead of generating new text. And that concludes the classification part of our tutorial. I hope you found it helpful. If you'd like to explore these methods further, visit the sites with the examples we've used here. You can modify the examples, experiment with different datasets or try other libraries. With each change, you'll deepen your understanding of the topic. So good luck and have fun. Meanwhile, the second major task in machine learning is regression, which we will explore next. But for now, let's take a break. After all, this video lasted more than 30 minutes. So it's high time for a break. I hope you liked this part, and if so, you could give it a like. AIs like likes just like people like. And thanks for watching this. You will find the next part of this tutorial on my YouTube channel. And if you want to get notifications about the newest videos I make, hit that subscribe button. Once again, thanks for watching and remember, improve yourself, improve your business, improve the world, but also live and have fun. Yours, Super AI.